In this video, we're going to learn about maximal flow models. Maximal flow models are a type of network model which allows us to determine the maximum amount that can flow from any given origin node to any given destination node in the network with capacitated arcs. The term capacitated arcs means that for each path or each arc that we draw on our network diagram, there is a limit on the capacity. So for example, if we consider two nodes A and B, and there is flow from A into B, if let's say that's a particular highway that we're considering, that there might be a capacity on the number of cars that can travel between nodes A and B on that particular highway. It could be capped at 200 cars, 300 cars, or whatever the specific number is for that highway. So basically, in this case, not only just your supply nodes have a capacity, but even the arcs have a capacity or a limit as to how much that they can accommodate on that particular route. It has been used to find the maximum number of automobiles that can flow through a state highway, or it could be used to help you decide if you're putting up a pipeline to transfer some product, let's say oil or gas, through a town. This can help you determine what the maximum amount that can flow through that system be. So let's take a look at an example that we're going to use to help us understand how to construct and how to solve for a maximal flow model. The example that we're using is the Waukesha road system in Wisconsin. So Waukesha is a small town in Wisconsin, and it's in the process of developing a road system for its downtown area. The city planner of Waukesha would like to determine the maximum number of cars that can flow through the town from the west. So you enter the town through the west point and you exit the town through the east point. The road network is what you see here in this diagram. The numbers by the nodes indicate the maximum number of cars in hundreds of cars per hour that can flow or travel from the various nodes. So for example, consider node number 1 as the visitor center for the town, and node number 2 could be the library. So if you enter the town, as soon as you enter, you see the visitor center, and from there are 3 different highways or roads that go into different destinations. So if you go from the visitor center, which is with what we've labeled as node number 1, to the library of the town, which is node number 2, the number on top of this arc, which is close to the node, will tell you what the capacity on that particular road is. So for example, from node 1 to node 2, in this direction, 300 cars can travel at a max. From node 1 to node 4, in this direction, 200 cars can travel at max. And then from node 1 to node 3, in this direction, 10 times 100, which would be 1,000 cars, can flow or travel within this specific route at max. So for example, if we look at node number 2 now, from node 2 to 1, now in this direction, backwards, only 100 cars can flow. So this could be a case where one side of the road has 2 lanes or 3 lanes, and the other side has only 1 lane, which is why the capacity on that side on that direction is lower, 100. If it's only a one-way road, which is in the case of node 1 and 4, from node 4 to node 1, you cannot go through this route, which is why the capacity is set to 0. One thing that you should probably note for a maximal flow model is that although it is a network model, but unlike the transportation and assignment models in which there are multiple origin nodes and multiple destination nodes, the typical maximal flow model has a single starting node. So that means there's going to be a single origin node and a single ending node or a single destination node. So for this Vacatia example, node 1 would serve as our single starting node or origin node, and node 6 would serve as our single destination node. All the other nodes in between are going to serve as transshipment nodes. So we have one pure supply node, one pure demand node, and the remaining 4 are transshipment nodes. Now, in order to formulate this example as an LP model, we have to modify the network diagram slightly so that we can account for the fact that these arcs can be bidirectional or unidirectional. So in order to do that, I'm going to change the network diagram slightly and distribute the arcs, which ones are bidirectional and which ones are unidirectional, by breaking them down. So from node 1 to 2, it was a bidirectional arc, which means you could travel either way. So I break down that one single arrow into 2 different arrows with the capacities written on top. If you remember, from node 1 to 4, it was a one-way road, which means you could not go from 4 to 1, which is why you only see one arrow and you don't see the other arrow going in the opposite direction. So if we break down each of the original arrows in our network diagram into these unidirectional arrows, it will help us determine how many decision variables we need in this case. So the revised network for Vacatia therefore is going to have 15 unidirectional roads. That's by counting the number of arrows that we have constructed in our modified network diagram. So as with transportation and assignment models, the presence of 15 unidirectional arcs in the network implies that there are 15 decision variables in Vacatia's maximal flow model. So basically you have one for each road in the network, which is how we can define our decision variables as xij, where x is the number of cars that flow or travel per hour on the road from node I to node j. So node I can take values which are given in our network diagram, 1, 2, 4, and so on, and node j can also take the values from 1 to 6. Of course, you should keep in mind that these decision variables are defined only if the roads actually exist. So for example, the road from 4 to 1 does not exist, so we don't need the decision variable x for 1. It's not going to be defined in our model, so we don't need to put it in there. Similarly, for example, x12 is defined because that road exists, whereas x15 is not defined because there is no direct road from node 1 to node 5. Now we need to determine the maximum number of cars that can originate at node 1, which is our origin node, and terminate at node 6, which is our destination node. All other nodes, like I said earlier, are transshipment nodes. However, unlike the transportation or assignment models, we don't exactly know the quantity of supply of cars available at node 1. Nor do we know the quantity of demand for cars at node 6. For this reason, we need to slightly modify the network further to set up and solve this maximal flow type of model. The modification which we're going to make means that we're going to create a dummy arc. Now, this dummy arc starts at our destination node and ends at our origin node. It's this particular arc that was not there in our original network diagram, but I just added this particular arc so that it helps me mathematically solve this model. Now, we call this a dummy arc because the arc, or this road, really does not exist in the network and has been created only for modeling purposes. The capacity of this dummy arc is set to an artificially high number. So for example, here I've set it to 1,000, which actually means 100,000 cars. This number, the actual number here, is arbitrary as long as it's really high compared to the other numbers in the model. Anything would do. You could set it to 20,000 cars, 30,000 cars, 100,000 cars, 500,000 cars. It does not matter because it's just a number that we need to assign for the model to be solved mathematically. So for every maximal flow model, you have to create this dummy arc, which is going to start at the destination node and end at the origin node. The reason why we do that is because if a car enters Waukesha, it's going to enter from the west point and it's going to leave from the east point. So in order to complete the circle, we have to create this dummy or artificial arc, which starts at the destination and ends at the origin. Now that we've defined our decision variables, let's talk about the objective function. The objective here is to maximize the total number of cars flowing into node 6. Now assume that there is an unknown number of cars flowing on the dummy road from 6 to 1. However, because there is no supply at node 6, the entire number of cars flowing out of node 6 here must consist of the cars that actually flowed into node 1. So basically, because we don't have cars automatically appear within this network, every car that enters, we assume that it leaves the system as well. So these two issues imply that if we maximize the number of cars flowing on the dummy road, that's equivalent to maximizing the total number of cars flowing out of node 1 as well, because the total number of cars flowing into node 6 would be what enters at node 1. So which is why when we define our objective function, it will just be simply maximizing the amount that is x61, which is basically the number of cars that can travel on our dummy road from node 6, which is the destination node, to node 1, which is the origin node. For every maximal flow model, you would have to create this dummy arc, and that dummy arc would also serve as your objective function. Remember, we have done this earlier as well, using the same variable as a decision variable as well as an objective function. We did that in our min-max and max-min problems. It's the same concept here. So this x61 is not only just a decision variable, it's also going to serve as our objective function. So far we have constructed our objective function and we've also defined our decision variables. Now it's the time to create our constraint equations using the same net flow balance equations. So as we remember from transportation and transshipment models, the net flow balance equations have to be one equation for each node in the diagram. So in this case we have 6 nodes in total, so that means you're going to have 6 constraint equations, one constraint equation for each node in our diagram. Let's take node number 1 first. So I'm going to call this N1 because this is the constraint equation that I need to write down for node number 1. So if I go back to my modified network diagram, you can see that in that network diagram, the inflow into node 1 is only from node 2, because there's only one arc that flows into node 1, and in addition to that, there is the dummy arc that we artificially created from node 6 into node 1. So if I use the formula that we use for net flow diagrams, inflow minus outflow is equal to the net flow for that particular node. Since we're considering node number 1, there are only 2 inflows into node 1. One of them is from node 2 into node 1, and the other one is from our artificial road from node 6 into node 1. That completes the inflow into node 1. So although node 1 is our origin node, but it's not a pure supply node. Instead, it's a mixed supply node because it has an inflow as well as an outflow. Now, let's move on to the outflow part for node 1. If you go back to the network diagram and look at it again, you'll see that from node 1, there's a road that connects it to node 2. There's also a road that connects it to node 4, as well as a road that connects it to node 3. So the total outflow from node 1 can be to one of these 3 nodes, which is to node 2, 3, and 4. That gives us basically the left-hand side of our first constraint equation. Now, because this is not a pure supply node, there is no capacity as such in here. In terms of how much can constantly flow across this particular node, we're going to treat it like a transshipment node. And if you remember from transshipment models, we said that whatever enters a transshipment node has to leave it as well because it's a temporary state. So we have to set it equal to 0, which means that if I rewrite this particular equation, it can simply be written as x21 plus x61 is equal to x12 plus x13 plus x14, because I just moved the outflow to the other side of the equation. You don't need to do this modification. This is just to explain, because in the book, this is how the constraint equations are written down. So I just wanted to explain how they got it there. They're simply using the inflow minus the outflow and rearranging the terms so that it looks like this. In the same way, we can write down equations for all of the other nodes as well. So let's take a look at the other constraint equations. For node 2, the inflow into node 2 was from node 1, 4, and 6 using the modified network diagram, and the outflow was to node 1, 4, and 6. And again, because all of these are transshipment nodes, really, they're not pure demand supply nodes, so we have to set them all equal to 0 for the right hand side. One more aspect which is also new to maximal flow models is that we do have capacity constraints on the maximum number of cars that can flow on each road, which is why you see a second set of equations on this slide over here. These capacity constraints make sure that on any specific road in one direction, the number of cars that flow are within the maximum capacity that has been given to us. So for example, the formatting here is a little off. So basically what they're saying here is that, let me fix that. Yeah. So X12 has a maximum capacity of 300 cars. X21 has a maximum capacity of 100 cars, and X61 which is our dummy road. We set the maximum capacity to a really high number, 1000. You can put 500 here, 20,000. As long as it's really high compared to the other numbers in the model, it doesn't matter. So you have to set that capacity to some level just for it to be able to mathematically solve it. The same way here, the formatting is a little off in this slide here, so I'm just fixing that. But essentially, we have the capacity which sets the maximum for each particular road in this case. Now that we have our full model formulation in this particular example, we can move on to our Excel template and fill out the functions and the formulas in there so that we can get this optimal solution using Solver. I've created the same table or matrix that we have been doing for transportation and transshipment models, node 1 to 6 on the columns here and node 1 to 6 on the rows, so that we can determine how many cars are going to flow on each of these roads here. So now, because the way we defined our decision variables, not all of these cells are defined. So I cannot select the whole box and label it in yellow, because if you remember from the network diagram, the road between node 1 and node 4 was only one way. So you could travel from node 1 to node 4, but you could not travel from node 4 to node 1, which means that this particular cell, which represents the number of cars that can flow between node 4 and node 1, we have to set that equal to 0. The same way, all the directions where the decision variables are not exactly defined, we can set all of those equal to 0. So for example, from node 1 to node 1, that does not really make sense, so we put that equal to 0. From node 2 to node 2 is again 0. 0 here. So the diagonal for this table would all be set to 0, and these are I'm manually typing them, so there's no function involved in here. Similarly, looking at our modified network diagram, we know that you can travel from node 1 to node 2, node 4, and node 3, and that's it. So you cannot go directly to node 5 from node 1, so I set that equal to 0 as well. And then finally, from node 1 to node 6 is also set to 0. The same way for node 2. From node 2 you can travel to node 4, you can travel to node 1, and you can travel to node 6. So from node 2, since you can travel from node 2 to node 1, I'll label that as yellow because that's going to be a valid decision variable. Similarly for node 1, I forgot to label those in yellow. And from node 2 to node 3, there's no direct road, so I'll put that a 0 over there. From node 2 to 4, there is a road, so I'll label that in yellow. And finally, from node 2 to node 5, there is no road. And from node 2 to node 6, there is one, so I'll label that in yellow. So basically, you get the pattern of what I'm doing. I'm only labeling those cells in yellow which are actually defined in our model, and the ones that are given 0 values are roads that are not defined in our model. Okay, so using that particular reasoning, I have now filled out my decision variables table here. Only the 15 nodes which are highlighted in yellow are our decision variables. The ones which have 0 values are not defined in our model, which is why we see the zeros over there. So like any other transportation or transshipment model, we'll calculate the flow outs for each node using the sum function, and I will copy this down without formatting so that it doesn't affect my template. And for flow in, it would be the sum of each column. So all the 6 cells under node 1. And I can copy this across without formatting. And now I can put labels on these cells here because they have formulas in them. So I'll put them in blue so that I can remember that these zeros were not added manually. They're because there's a function in there, there's a formula in there, which is why they turn out to be equal to 0. So the table right underneath our decisions variable table defines the capacities for each of the node to each of the other nodes. So the capacity for each road is given in this particular table. Because the road from node 6 to node 1 was an artificially created dummy node, I've added a capacity of 1000 multiplied by 100, so 100,000 cars in this case, and I added that number in here just to represent that artificial dummy node that we created. In actuality, this number does not exist. It's just for us to help us solve the model mathematically. So our objective function is to maximize x61, which is also one of our decision variables. So you just have to set this cell equal to this number here, x61, and that will be our objective function. So there is no sum product function for this particular type of model. And because it's maximal flow, we have to maximize this number here. And again, there is no sum product function. It's just the dummy node or the dummy road that we created, which starts at node 6 and ends at node 1. In a more general case, it will always start at your destination node and end at your origin node. So now we have our decision variable in, and we also have defined our objective function. Let's fill out the constraint equations. The flow ins into each of these nodes are given in these cells here. So 3, node 4, node 5, and finally node 6. And then the flow out is given in these cells here. For the flow outs, I can simply copy it down because it's in the same format as, because this is also in a column and this is also in a column, I could copy it down. For the flow ins, these were in rows and these were in columns, so I couldn't copy it down, so I had to do that manually. The net flow is going to be equal to the inflow minus the outflow, and I can copy this formula all the way down. Now, because all of these contain functions in them, none of them have been manually added, I'll put my blue labels in here. And because, again, this is going to be a balanced model, I can put an equal sign for all of these constraints, and the right hand side value is set to 0 for all of these nodes because they all act like transshipment nodes. So that completes our flow balance equations. For the constraint equations, you can simply add them into Solver. You don't have to include cells here to represent the capacity constraints for each of these nodes. We'll put them directly into Solver. So let's go to Solver, and here in Solver, our objective function is to maximize cell C22 subject to changing variables from B5 to G10. Now, I know that we only define certain cells in this box here, which are going to be our decision variables, and those are in yellow. But you don't have to individually type those out. You can select this whole box, and the way Excel would know which ones are actual decision variables is using these numbers here. So the ones which have the capacity of 0, Excel would automatically drop them from being decision variables. So that makes this whole selection of decision variables in the changing cells part of Solver really easy. You don't have to individually type the yellow cells. You can just select the whole box, and Excel will automatically determine using this lower box here which ones are decision variables and which ones are not defined. So I've already added my net flow equations in here. So this second line of constraints is that M5 to M10 have to be equal to O5 to O10. And if I move this cell here, you can see that I'm referring to column M and column O. Oops. Okay. The second set is for the capacity constraints. Because we said that the capacities are determined here by the second box, you can simply select the first box to be less than or equal to this second box here, and that satisfies the capacity constraint. Check the non-negativity, select simplex, and click solve, and we get a solution. So the maximum number of cars that can flow, here it says 5, but we know the way we defined our model and constructed it, this means 5 times 100, so 500 cars can flow at the same time in 1 hour in the road network that has been set up for Vocatia.